All right, we're going to introduce a new idea. We're going to do something called the matrix inverse. And what we're going to do is start off with a quick example, and it's going to be a little mysterious where things are coming from, but then we'll use this example to try to motivate how we can actually calculate an inverse if it exists. So let's start off. Suppose we have 3x plus y is 4, 2x plus y is minus 1. I know I can write this as a matrix times my state, which is xy, which gives me a vector. And the coefficient in the first equation, the coefficient on x is 3, the coefficient on y is 1. So I have 3x plus y equals 4. Second equation is 2 times x plus 1 times y is minus 1. What if, and I know you're probably thinking this, I take my equation and I multiply a matrix on the left-hand side. Suppose I try this matrix. So if I do this on the left, I have to do it on the right. Let's see what happens. So I'm going to do the matrix inverse. I have 3 times 1 plus 2 times minus 1 is 1. 1 times 1 plus 1 times minus 1 is 0. Minus 2 times 3 is 6, plus 3 times 2 is 6 is 0. Then a minus 2 plus 3 is 1. And on the right-hand side, I'll have 4 plus a minus 1 is going to be 5. Then I'll have 4 times minus 2 is minus 8, minus 3 is minus 11. Now notice if I multiply this, I have 1 times x plus 0 times y. That's just x. And I have 0 times x plus 1 times y is 1. There's y. So I immediately get that the value of x is 5 and the value of y is minus 11. So your thoughts on multiplying by this matrix were pretty good. That was a good choice. But what happens if how do I know that happened, or what that's going to be? I don't know yet. So we're going to need some definitions and figure out what's going on. But if I'm given a matrix A, and I have another matrix B, and I get A times B is the identity matrix, then we'll say B is the inverse of A. And we'll oftentimes denote this as A inverse as A, and use minus 1 as a superscript. This is not an exponent, it's just notation. Okay? And there's going to be an important caveat is that not every matrix has an inverse. So we'll oftentimes say if the matrix exists, then certain things are nice and can happen. Okay. All right. But the key thing here is that if the inverse of a matrix A exists, then A times its inverse is the identity matrix. It's going to be important that A is a square matrix. So the number of rows is equal to the number of columns. And that's going to imply that A inverse is a square matrix. And that's because I has to be a square matrix by definition. So where did this come from? How did I get this beast? Okay, well, let's back up. My original matrix was 3, 2, 1, 1. And I want 3, 2, 1, 1 times something is going to give me the identity matrix, right? What the heck does that mean? So that means I'm looking for some matrix, we'll call it B, and it has entries B11, B12, B21, B22, so that when I do this multiplication, I get the identity matrix. The way we have defined matrix multiplication is that if I go across this row and down this column, that gives me this entry. If I go across the second row in the first column, that gives me that entry. That means this matrix times this column gives me 1, 0. Same thing is true for here. If I take 3, 1, 2, 1 to get 0, 1, I'm multiplying by B1, 2, B2, 2. All right, so 3 times this plus 1 times this has to be 0. 2 times this plus 1 times this has to be 1. I'm really solving two different systems of equations. I want to solve that system equation. I want to get B11 and B21. Then I want to solve this system of equations for B12 and B22. Note I could put this in an augmented matrix. All right, for equation 1, I could put it in that augmented matrix, and then for equation 2, I could put it in that augmented matrix. I would then go through and do the row operations to put this in reduced row echelon form so that I would get this. I would then do the exact same thing with this to put it in reduced row echelon form. But the thing is, when I do the row operations on this, it's going to be exactly the same row operations on this. I'm going to do the exact same thing because I'm looking to get the exact same result. The only thing that's different is going to be what happens in here. So that means I can basically do this all at one time. If I put my augmented matrix is going to be exactly the same now. The only difference is now I'm going to do this second operation at the same time. And my goal is to take this, turn this into the identity matrix. And if I can do that, the result here is going to be my B11, B21. My result in here is going to be my B12, B22. And if I can put this in reduced echelon form and get an identity matrix, then whatever's in there is going to be my inverse. We've already seen that we can't always do that. So this word if is going to play a big role in what we're doing. If that happens, then we can get the inverse. So let's see if we can do that. So we had A is 3, 2, 1, 1. We claim that we should get that for the inverse. But the question is how did we get that in the first place? Well, let's take our matrix. And we're going to create a new augmented matrix. The only difference now from what we did before is that this is an identity matrix on the right. And I'm just going to cram it through. So this is my pivot. I want that to be a 1, so I'm going to take 1/3 times row 1. And I'm going to leave row 2 alone. So if I take 1/3 times 3, I get a 1. 1 times 1/3 is a third. 1 times 1/3 is a third. 0 times a third is 0. This is still my pivot. I'm going to make zeros below it. So to do that, I'm going to take row 2, and I'm going to subtract a factor of 2 times row 1. So I'm not changing the first row. So 2 minus 2 times 1 is 0. 1 minus 2/3 is going to be 1/3. 0 minus 2 times 1/3 is minus 2/3. 1 minus 2 times 0 is 1. I'm going to the second row. This is my new pivot. I want that to be a 1. So I'm going to multiply the whole row by 3. So I'm leaving the top row alone. So I'm going to have 0. 3 times a third is 1. 3 times minus 2/3 is minus 2. 3 times 1 is 3. So I'm going to use this pivot to get zeros above it. So I'm going to take row 1, and I'm going to subtract a factor of 1/3 of row 2. So I'm leaving the bottom row alone. So 1 minus 1/3 times 0 is 1. 1/3 minus 1/3 is 0. 1/3 minus 1/3 times minus 2. It's going to be 1/3 plus 2/3 is 1. 0 minus 1/3 times 3 is minus 1. And there it is. My A inverse is exactly what I was hoping it was going to be. And notice I was able to get the identity matrix there. Again, if this had been a 0, that means the inverse does not exist. Let's do another example. Okay, so in this example, we have the matrix B, which is 2, 4, 4, 1, 1, 2, 0, minus 1, 2. And we want to find the inverse, if it exists. So it might not exist. So I'm going to take the matrix and write it down. Now to form my augmented matrix, next to that I'm going to write an identity matrix. So 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm going to put this in reduced row echelon form. If I end up with an identity matrix on the left, then whatever I have there is going to be my inverse. If I cannot get an identity matrix on the left, no inverse exists. So let's go with find my pivot. Pivot's going to be start off there, and I'm going to try to make zeros below it. So to do that, I need a 1 there. So I need to multiply everything by a half in the first row. So 2 times a half is 1, 4 times a half is 2, 4 times a half is 2, 1 times a half is a half. I get 0 halves, 0 halves. I'm going to leave everything else alone. And now, this is still my pivot. I'm going to get zeros below it. So I'm going to use my pivot as row 1. And I want to get, when I'm done, I'm going to leave the first row alone, and I know I'm going to have a 0 there. And I know I'm going to have a 0 there. So to get a 0 here, I'm going to take 1 minus a minus 1. Minus just row 1. So that means 1 minus 1 is 0. 1 minus 2 is minus 1. 2 minus 2 is 0. 0 minus a half is minus a half. 1 minus 0 is 1. 0 minus 0 is 0. Okay, now to get a 0 here, there's already a 0 there, so I'm just going to leave it alone and do nothing. This is now my new pivot. So when I'm done with this operation, the first row will be the same. I'll have a 0 there, and I know I'm going to have a 1 there. So I can do that by dividing through by a minus 1 everywhere, or just taking minus row 2. So that'll give me a 0, 1, 0, minus a half is 1 half, minus a minus 1 is minus 1, minus a 1 is 1, minus 1, minus 0. I'm going to leave the bottom row alone. This is still my pivot. I'm going to get zeros underneath it, which means I need to get a 0 there. So I'm going to leave the first 2 rows alone, and I know that I'm going to put zeros there. So I'm going to take row 3. My row pivot is 2. So I'm basically just going to add those or subtract a minus and negative of that. So just if I add these 2 rows, I'll get a 0 there. 0 plus 0 is 0. 1 plus minus 1 is 0. 0 plus 2 is 0. 0 plus 2 is 2. 1 half plus 0 is 1 half. Minus 1 plus 0 is minus 1. 0 plus 1 is 1. Okay, so now my new pivot is right here. So I'm going to go down the next row, which means I'm going to leave these 2 rows alone, but I know that I'm going to have a 1 here, and the way to do that is by taking 1/2 of row 2. So 1/2 times 1/2 is 1/4. Minus 1 times 1/2 is minus 1/2. 1/2 times 1 is 1/2. Okay. So that's a lot. So I started off with my matrix B. It's 2, 4, 4, 1, 1, 2, 0, minus 1, 2. I put this in an augmented matrix where I had the original B there and the identity matrix there. I started doing row operations, and I ended up with this augmented matrix. Is that correct? I think that's correct. Okay, and I was going downwards, so this becomes my new pivot. And now I want to put zeros above everything. So I'm going to leave the bottom row alone. I know that I'm going to get a 0 there, but there's already a 0 there, so I'm going to just leave that alone. Now I know that there's going to be a 0 there when I'm done. So what I'm going to do, I'm taking row 1 and I'm subtracting off something of row 3. I'm going to subtract off 2 of row 3. So I'll have 1 minus 2 times 0, 2 minus 2 times 0, 2 minus 2 is 0. 1/2 minus 2 times a fourth should give me 0. Let's see. Is that correct? Yes. 0 minus a minus 2 times 1/2, which gives me a 1. Then 0 minus 2 times 1/2 gives me minus 1. So I have zeros above my current pivot, so I'm going to shift left. So I'm going to go up a row, and this is now my pivot, and I'm going to get zeros above this. So I am leaving the bottom row alone, the middle row alone, and I know that when I'm done, I'll have a 0 there, and I should have a 0 there if everything went right. So I'm taking my row 1 and I'm subtracting off 2 of row 2. So I'll get 2 minus 2 times 1 is 0. If I do that, I get 1 minus 2 times 0. 2 minus 2 is 0, so that's right. 0 minus 0, so that's right. Get 0 minus 2 times 1/2 should give me a minus 1. 1 minus a minus 2 times minus 1 gives me a 3. And minus 1 minus 2 times 0 gives me a minus 1. So that means my B inverse should be, oops, I messed up. I wrote, that should be a 1, right? Because that gives me 1 minus 2 times 0. I was looking at that and thinking ahead. This is an identity matrix. I'm in reduced row echelon form. So whatever is here, which is minus 1, 3, minus 1, 1/2, minus 1, 0, 1/4, minus 1/2, 1/2, should be my identity matrix. And I can do a quick test, see if this is right. So I take my original matrix, and if I multiply it by this matrix, so I'm not sure that's really the inverse yet, I should get an identity matrix. If not, I screwed up. So 2 times minus 1 is minus 2, plus 4 times 1/2 is 2, so that's 0. That's 0. 4 times 1/4 is 1, so 0 plus 1 is 1. So that's good. To get this entry, I'm going to go across the first row down the second column. So I have 6, minus 4 is 2, minus 2 is 0. And for this, I'm going to go down across the first row down the second column. I have minus 2 plus 0 plus 2 is 0. Okay, now I'm going to basically do the same thing, but I'm going to now use this middle row. I'll have minus 1 plus 1 is 0 Oops. We have -1, oh, plus a half is 0. Whew. Now I have 3, -1 is 2, -1 is 1, so that's good. Now -1 plus 0 plus 1 is 0, so far it's looking good. It's looking like the identity matrix. I'm hoping to get a 0, 0, 1 there. So now go and cross the bottom row down the first column. I'll have 0, minus a half plus a half is 0. And here I'll have 0, 1 minus 1 is 0. And now 0 plus 0 plus 2 times a half is 1. And that is indeed the inverse. Okay. And again, you basically got to check everything, and you should be able to check this in the end. And because I had 1, 1, 1 on the diagonals and everything else was 0, that means I had the inverse. So we can ask all kinds of questions. Suppose I have a matrix that's a product of two matrices C and D. And let's suppose C is a square matrix and D is a square matrix, and C inverse exists and D inverse exists. I can ask, what is the inverse of CD? And so now here's the thing, notation is going to be an issue here. C times D is a matrix. And so what I'm looking for is the inverse of that whole thing. So I am looking for something that when I multiply it, I get I. So here's the thing. What goes here so that when I end up with I, but notice if I just focus in on those two things, if I were to get an I there, I would be left with something times the D. And then, because whatever here is times I is going to be whatever this is. And then I immediately see I could put a D inverse there. So if I could deal with this right here, if I could make that an identity matrix, I can figure out this whole thing. But I know that C inverse exists. So if I make that a C inverse, that's the identity. And then I times D is just D. And so then if I put a D inverse here, then I'm going to end up with the identity. So let's look at this another way. That's going to be confusing. I am looking to figure out how to multiply something times CD to get the identity matrix. If I work inside out, C inverse times C is identity matrix, and the identity matrix times D is just D, so I get that. So my claim is that D inverse C inverse is the inverse of CD, and the way to check that is basically just multiply this thing times CD and see what I get. What I can write this as D inverse times that in the middle, but this is just the identity matrix, but I times D is just D, so I get D inverse D, but D inverse D is I, so that is the inverse. Okay, and it's important to recognize that where did this come around from? And that is that if I have AX equals B, my goal was to figure out what X is. And if I have AX equals B, if this is a big if, A inverse exists, and if I multiply both sides on the left by A inverse times A A inverse times A is the identity matrix. I leave the right-hand side alone. I times X is just X. And I can just immediately figure out what the solution is to my system of equations.